all, we are talking about communication systems. We start from the very beginning, very easy one. So we talk about amplitude modulation first. Then we talk about FM and PM, frequency modulation. Then phase modulation in chapter 6. Remember at the very first introduction part, we talk about modulation. This is unique for communication. So we're going to discuss what is modulation and how can we do this AM. So modulation, we are talking about two kinds of signals, modulating signal and carrier wave. So this one, modulating signal, we look them as passengers, something you want to transmit. Carrier wave, we view them as vehicles or different transportation methods. For example, this is somebody, right? This is Eric. He wants to go to Chicago, right? So he can choose take the train, right? Take buses, or drive, or even just ride his bicycle. So when there is signal, there will be something we have to transmit. So we have. This one will be information you want to transmit, either your voice, your music, text messages, images, video. And carrier wave, you can choose different carrier wave. And depending on different carrier wave, you have different kinds of modulation. So we try to put signal on carrier waves. So carrier will carry information, transmit to the other side, transmitter. So at receiver side, we do demodulation. Passenger will take off from those different vehicles. So at transmission side. Modulating signal will kind of, we put modulating signal on carrier. Carrier will transmit it through the air, then at the receiver we have information back, right? So we call this part modulation, the other part demodulation. So here we go. And in at home, right, you have modem. So modem can do modulation, and so modem means modulation, and you have a cable modem, right, or DSL modem, or very beginning those dial-up modem. So two procedures very important: modulation and demodulation. Only in communication systems, signal processing we don't need to do that, right? And power system, we don't have to do modulation and demodulation. So based on this one, based on carrier, we divide them into two different catalogs. One called continuous wave, CW. Another one called pulse modulation. So we're going to show examples of what is continuous wave, what is pulse modulation. So both of them, they're pretty popular. And for this book, we focus more on continuous wave modulation. Pulse modulation is also very popular. but most likely used for digital signal communication. So here we have two examples. This is my signal, right? Modulating signal, my information, and B is continuous wave. We have a continuous, right, sinusoid wave, and this one is changed according to your shape of the information. So we can find my amplitude is changed. We call it AM. So this one is continuous wave modulation, and AM. This one, now we have multiple impulse signals. So we call this one pulse modulation. Here we change the pulse amplitude. Later we talk about pulse can also change the width, so we call the, so this one is PAM. Later we talk about PWM, so the width of your pulse can be wider or narrow. We also have PPM. Position of your pulse can be towards the forward or towards the end of this period. So we have PAM, PWM, PPM. For continuous wave, right, we have pulse. For continuous wave, we have AM, FM, and PM. So later we show we can not only change amplitude, we can also play with different phase, different frequency. And if we combine amplitude and phase, we have QAM. So we can have phase and amplitude change together. Chapter 5 and 6, we talk about continuous wave modulation. Chapter 7, we're going to discuss pulse modulation. So here just a kind of introduction. Any problem? Any question for the two categories, continuous wave and pulse modulation? So why we want to do modulation, right? There are some benefits. Number one, efficient transmission. So sometimes, right, if I talk, right, you can hear. If I talk even louder, maybe somebody in the hallway can hear me. But far away, right, they cannot hear me. But if we change our signal into something and transmit it audibly, can also hear this lecture. So more efficient transmission. We can modulate the signal into different carriers and transmit them. Overcome hardware limitations, and also overcome some limitations in your system and environment. So you can move your signal to any band you're interested. For example, I want to use free band, right? I don't have to pay the license fee. So this is also another benefit from modulation. Reduce noise and interference. So especially the interference. So this is also a benefit of modulation. You can choose those bands have less interference. So make sure less interference. And if we have time, we can also talk about CDMA, right? So how can we reduce interference in the same band? Use modulation method. Okay, frequency assignment, we already talked about that. We already talked about this one, right? So we can choose those frequency band or those channel, good or fit for your requirement. For example, you really want good reception, right? You may want to choose the paid, right, band. And if you don't care about that so much, and you can choose those free band. Last one actually is a really important one, multiplication. By using modulation, we can transmit information, different signals simultaneously. So we call it multiplication. Very soon we're going to talk about how can we do multiplication in frequency, in time, and also encode. So those are some benefits bring by modulation. So everything has pros and cons. Cons will be make our system more complicated, right? So cost a little high. Okay, so now we talk about the important stuff. AM. AM we consider is the simplest modulation method. Compared with PM and FM is much simpler. So continuous wave, right, we use a sinusoid. This is a typical sinusoid signal. We have AT as amplitude, theta t as the phase angle. So, okay, we write this one. A of t is my amplitude, or we call it envelope. So, right, the shape of your amplitude. Omega c, later we call it, this is the vehicle. And omega c determining where is the vehicle, right? Very high frequency or very low frequency. So if you talk about, right, I'm use short wave or medium wave, right? Or microwave, depending on omega c, what is your carrier frequency. And gamma t is something we can play with here in this brace. Okay, so if I play with this A of t, keep omega ct, gamma t constant. We keep omega c and gamma t as constant. We only play with A of t, we call it AM, amplitude modulation. So let me talk about if we keep A of t the same, but play with gamma t, omega ct, we are going to call them FM and PM. Okay, so this one I want you to remember omega c determine which band you are using. What is your central frequency of your modulated signal? So here, we don't change gamma t at all, right? If gamma t is 0 or constant, so we have a pure line, sinusoid here. But the amplitude is a variable, right? If ft is my signal, is my modulated signal, we call the entire equation AM, amplitude modulation. So my amplitude is a variable. The amplitude will carry my information in it. So this is the definition for amplitude modulation. Later we play with this equation and we have different catalogs of AM. AM actually is a family. It has 4 members. We're going to discuss different members one by one. Okay, this is the first one. We call it amplitude modulation, large carrier. Large carrier from here, right? This is previous equation we used, and we add something to it. A cosine, we call this one large carrier. And why we do it? This one can make our reception very easy. So we talk about that very soon. So if this is my signal in time domain, very easy for us to find the Fourier transform of it by properties, right? By properties. And pair Fourier transform. So if you look at the Fourier transform of given signal, we have F omega, right? Your signal spectrum, however, move to right by omega c, to left by omega c. So this is called AM. Then we talk about large carrier. We have impulse, right? At minus omega c, another impulse at omega c. Those two large carriers. Okay, equation may be not clear enough.
Yeah, how did that work with both impulses?
Yeah, A cosine omega c is Fourier transform. I have two impulses. This is from the table. Okay, yeah. We have the picture, we have figure. If my signal is something like this and it's spectral, F omega, it's something like this, like a bell. So I have my signal, if modulating signal in time and in frequency. Here, signal mixed with sinusoid. So here, ft times cosine omega c we can find, right? I still have my sinusoid here. However, the envelope is changed according to your message. So this is what happened in time and in frequency. Now my spectrum moved, right? Moved to omega c and minus. Okay, minus omega c just a concept. We know that there is no negative frequency, right? So if you look at it in spectrum analyzer, only this side, this side. So theoretically, there also another band over there. So you choose omega c, right, by your application. Channel 1, right, channel 2, channel 3, you just choose omega c, you just move it over there. Now, the carrier, right, A times cosine omega c, we have a sinusoid. And this one's Fourier transform, like he just asked, two impulses. So we mix them together, we add them together. This is my frequency domain. So this is my time domain. So I have this one kind of right, like expand, right, in y-axis. So I have my large carrier signal in time. This is in frequency. Why we do it? We just mentioned, right? Make our reception very, very easy, very, very easy. So quickly, I just show you what can we do for this kind of signal. Then we go back to talk about all the So why it is maybe the next week I can talk about this. So for double sideband, large carrier AM signal, something like this, we can use a very simple circuit. A dial, capacitor and resistor, we get the information out. You don't even need a power for it, right? So very, very simple. Right? So let's look at what can we do here. I know envelope carry my information. So if I can extract the envelope, I know the information. Okay, this dial will remove all the negative frequency, right? Dial. Then we have capacitor. So when my input signal go up, this capacitor is charging, right? So my output voltage also go up. When my input goes down, it will discharge, slowly discharge, right? Discharge. And then it go back again, so it's discharge, discharge, charge, discharge. So we have charge, discharge, charge, discharge. If I can choose my R and C very carefully, very cleverly, I just catch the envelope. So we call it envelope detector. This technique can make my receiver very, very simple. So means I can have millions of customers, right? They just pay $1, $2 per receiver. So even I add something here, later we will find it's not very efficient. However, the good thing is a diode, a capacitor, a resistor can get this envelope. Okay, now we go back. This one we are going to come back again later. Any problems, questions? Okay, so let's go back to double sideband, large carrier. Okay, later I'm going to ask you plot signal in frequency and in time. So any problem for this one? Time and frequency. Okay, like look at carrier. So we have signal. We have just carrier. So how big we should choose this large carrier? So we are going to give it a term or a definition. So depending how big your carrier compared with your signal, we have a new definition. We call it Modulation Index. So this one tells you how big your signal or how big is the large carrier. One thing I want to mention, previously we have ft here. We use cosine omega m of t for the message. Just try to make our analysis. This is my so here cosine omega m of t is the message. We rewrite it a times 1 plus m cosine omega m of t cosine omega ct. So my message, my message kind of modified by this m. One will be normalized big carrier. So if m is bigger means compared with the carrier, my signal is also big, right? If m is a small number, means compared with the carrier, my signal is small. So m is really important parameters you can play with. Generally, m in commercial broadcast, AM broadcast, around 0.7%. So this is how can I find modulation index. Later we show example how can I find m from a given signal. Then we show several examples. So for different m, my signal will look differently. This is message, right? This is message. This is carrier. And most likely, frequency of your carrier is much, much higher than the information. And here is m times a message and carrier. So when m greater than 1, we call it over-modulated. This is something we do not want happen. When m equal 1 or m less than 1, something we really want. So why? Because when m less than 1 or m equal 1, my envelope is exactly my information, right? So we can use envelope detector to extract envelope to get my message. If something happens like this, even I extract the envelope, my signal change, right? My signal change. So generally M will be less or equal 1. And we choose less than 1 because there will be some guard here. So generally M will be a number less than 1. Then we talk about a very important problem. So if you have a cell phone, right, what will be top 3 concern you have for the cell phone?
The reception and reliability.
How about battery?
Okay.
Yeah. So we talk about not only bandwidth is important, but also power consumption, energy consumption, very important, right? We do not want to charge my battery every 2 hours, right? So power consumption is very important. We want the power used to transmit useful information, right? Not this. So we talk about very important thing in communication systems, the power for my signal. So 2 things we are really care about. One is the total power, how much I should use to transmit my signal. Second, is this transmission very efficient or kind of waste my battery or waste my money? So for double set large carrier AM, we talk about those 2 things. So this is my signal, right? How can I find this signal's power? We know, right, from chapter 2. Average power also mean square value, right? Mean square value. So we calculate mean square value or power for this signal. Okay, so we have power calculated. This one we know is half a square because cosine omega ct square will be half 1 plus cosine 2 omega ct, right? We talk about. Okay. We know cosine 2 omega CTT integral on periods we get 0, so we get half, right? We get half. So the first part we get a square, half a square. The second part we get half your signal's power, so half came from, right, this part. Total power will be half a square. Remember, this one just carrier. This one is for a message. So we call this part PC, power for carrier only, and PS, power for signal. And this one is something we use, right, efficiently. And this part will be waste.
So the 2 equations are the same?
Question, same?
So the 2 equations are exactly the same, the average power and the total power?
Yeah, right, the same. The total power and the average power. If I ask average power, will be the same as total power. In our textbook called average power, total power, so the same concept. But if I ask power for carrier, will be part 1. Carrier for sideband or carrier for signal will be part part two. So we want to know that I use power from my battery, right? Energy from my battery. What is the percentage useful? So we call it power efficiency. We use mu. So mu is PS over PT. Total power, right? Here is sideband power or power for the message. So we just plug in, right? This is power for message, right? This is the total power. Half cancel, right? Half cancel. So this is the initial equation. Once my signal is a special signal, sinusoid, we can simplify this equation. Mu is only related with modulation index. And we are going to show one example. How can we calculate total power? How can we calculate power efficiency in next example? So we're going to go back to those equations later. Okay, any problem for this one? Total power. Half from cosine omega ct, right? Another half from cosine omega m of t. Okay, so let's look at one example. Example 5.2.1. So a given AM, we use double sideband large carrier broadcast station, transmit average power, carrier power output 40 kilowatt. Really huge, right? Actually for those commercial radio stations, the power is really huge, 40 kilowatt, a big number. And use modulation index 0.707. This is typical commercialized radio station use. M is 0.707. So let me write down those things for you. PC is 40 kilowatt. M 0.707. For sine wave modulation, so my f of t is cosine omega. My signal is sinusoid. We want to find three important things. Number one, the total average power output. So A will be PT, right? What is PT? Number two, the transmission efficiency. What is my mu? Okay, last one. The peak amplitude of output if antenna is represented by a 50 ohm resistor. So C, peak. R 50. So we're going to find total power efficiency, peak value of the modulated signal. So what is PT, right? We just write down PT is so. Okay, let me write the original one first. A 1 plus M ft cosine ct. This is a double sideband large carrier modulated signal. So now my ft is sinusoid, right? I rewrite it as this one. My total power will be m squared, right? Oh, and a squared. So this is carrier, right? Half from cosine omega. So I have half a squared is my PC, half m squared, m, right? Cosine omega mt power. We know it's half, right? We write it split. So half a squared plus half m squared. A squared. Okay, any problem for this one? How can I get this one? First half from cosine omega c. Second half from cosine omega m. M I just copied, right? A is the amplitude of my carrier. Okay, we call this one PC, right? We call this one PS. Okay, I'm going to write one more step. Let me know if you have any questions. Any problem? Any problem for this one? You're fine, right? So PC 1 plus half 1707 squared. PC is given, right? PC is 40 kilowatt. 40. So I have 40 times 1 plus 50. My total power is 50 kilowatt. So in your textbook, they have PC. PT is PC plus m squared over 2. So PT is 50 kilowatt. This m squared over 2 because all those steps. So my total power is 50 kilowatt. When I transmit a sinusoid wave to m.707, my average output power will be 50 kilowatt. Really huge, really huge. If you touch, right? If you can touch, right? Actually, you cannot. If you can touch the antenna, will be freaking cold. So because all the power kind of transmit outside. So now, any problem for part A? How can we find this one? Second, efficiency, right? Efficiency will be PS over PC, right? So PS over PC. Oh, no, I'm sorry, not PC over PT. So will be m squared, right? Half m squared. 1 plus half m squared. Half a squared. Right. Half a squared cancels. So we have half m squared over 1 plus half m squared. So this is half 1707. My efficiency is 20%, 20%. So 50 kilowatts, only 10 kilowatts are used for my message. Okay, yeah. My efficiency is 20%. So pretty low, right? Pretty low. So it means you charge it, right? Okay, only use for 1 hour. So something like that. So efficiency pretty low. Those, any problem for part two? How can we get this 20%? The last one, I'm going to explain this one a little bit. I'm going to have a sketch for this modulated signal. Okay, I use dashed blue color for my envelope, for my message. So inside the envelope we can find my carrier still sinusoid, but the envelope changed according to your information. So it goes high to peak, right, and goes low to like the valley. How high it is depending on two things, right? Depending on, if you look at this one, how high it can achieve depending on A and M, right? How low still depending on A and M. So the top level, the highest maximum I can achieve, I call A max or A peak. So I have a max value and a minimum value. Right. When my signal is positive 1, I achieve the highest point, A 1 plus M. So half. When my signal is positive 1, normalized, when my message is positive 1, and A minimum, A 1 minus M. Minus sign came from, this time my message will be minus 1. So A max, A minimum depending on A and M, because my FT will be normalized. Any problem here? So here, right? 1 plus MA. 1 plus M came from over there. How can we find A? Power, right? Power. So PC. PC is here, right? PC is half A squared. If I know my resistor value is 50 ohm and my A is a voltage, so there'll be V squared over R, right? So V squared over R is 40K. Then solve this equation, we get, let me write one more step for it. So PC is A squared. Okay, right? So PC, A squared over 2R. A squared will be PC time 2R. PC is 40, right? 40K becomes the third. So A squared is 400,000, right? Oh no, 4 million. 4 times 10 to 6, 4 million. So A should be plus minus 1. And the voltage, amplitude, right? They choose the positive sign. My A is 2,000. So A we choose 2,000 volt. This is how high you think can achieve, right? 2,000 volt. Really, really high amplitude. And A max is A 1 plus M. The 2,000 1 plus 0.707, we have 3,400 volt. So 3,440 volt. So now I show you step by step for part A, B, and C.
So in this case, why are we dividing by R? Why are we dividing by R in this case? Is our signal a voltage signal?
Yeah, because yeah, the total power we know is 40 kilowatt, right? 40 kilowatt. And A is a voltage. A is a voltage, so divided by R. But if you consider if you consider it is your current will be also very, very high, right?
Okay.
Yeah. So
it's kind of like B squared over R. It's a half of that
because of your signal is not a DC, it's a sinusoid. Half from cosine omega CFT.
Okay.
Right, yeah.
Thank you.
Yeah. Because this is AC, right? It's AC. So any problem later in your homework, we are going to calculate total power efficiency. Yeah. Do we have? Yeah, maybe. I'm not sure if they have any problem in homework. Calculate. Yeah, but anyway, right? So if you know A, you can find your A max and A minimum, right? If you know A and M, you can easily find the maximum and minimum in your signal waveform. Any other problem for this example? I'm going to show more examples. So we are going to, I'm going to show you 2 more examples. Here, my efficiency. So we are going to focus on this one. Efficiency. Efficiency is not, it's not very good, right? It's not very good, 20%. In real applications, it's even worse. So we show you the best we can achieve and a general case. So for AM, double sideband, large carrier. Example, we call it number 2, right? This is P. 1 minus 1. And we choose. If I have a square wave, my amplitude is 1 minus 1. This is my period. I choose the biggest modulation index I can use, m equal 1. Let's look at what is the mu, right? What is the efficiency? How good I can achieve. This is the best case we can achieve for double sideband large carriers. So how about my efficiency? Okay, what is my power? It's 1, right?
Yeah.
My power is 1. My power is 1. Okay, efficiency. Let me write down. Okay, total power will be half a square plus half a square m square. Okay, this is a general case, no sinusoid anymore. So A 1 plus m ft cosine minus t. So the total power will be half a square for the pure carrier and half a square m square. Your signal power, right? Your signal power. So this is my total power for a more general case. This example, my signal is sinusoid. So mu will be PS over PT, right? So okay, half a square will be the common part, so cancel, right? Cancel. So the amplitude of your carrier does not affect your efficiency. However, M does play a very important role here, and also your signal is important. So in this case, my message power of any problem, how can I get this one? Let me talk about this specific problem. Okay, so in this case, my M is 1, right? Power of signal is also 1. So I have 1 plus 1. 50% will be the highest efficiency I can achieve for double sideband AM. Because M you can only choose any number less than or equal 1. And since my information is normalized, so the power for message, the highest we can achieve is also 1. It's also 1. So 50% is the highest you can expect.
does the bar mean over that?
F, which one?
The bar of the.
Oh, this means mean square value. Mean square value. Also power of message. X mean square. Mean square value. Means square, then the average. Okay, so now we are going to look at a real case, a real signal transmitted by using AM broadcast. So example 3. We have 3 here. So this time we have video broadcast signal. We're going to choose f equal 0.707. This is the typical modulation index people use, 0.707. So actually not a very small number, right? Pretty big. Message. Modulating signal. Okay, and the modulating signal f of t will be either voice, right, or music. So this kind of signal, not like sinusoid, not like square wave, is it's like a random one, like noise. Also PF. The power of this kind of signal, either music or voice, if we normalize my signal to 1, the power of it is around 1. Oh, I'm sorry, not 1, around 0.1. So my power for a speech signal, normalized power, normalized signals power will be around 0.1, just 1/10 compared with square wave. Now let's look at my efficiency. 1 square. So 0.707 square. Okay, this time my message power is around 0.1/10. So I substitute my m and the f square bar into it. What is my efficiency if you have a calculator? We have if you have a calculator, you calculate, right? I have the answer, but I want you to just